Now that we know our fundamental identities for our trigonometric functions, we can do something referred to as verifying trigonometric identities. So what that means is that you're going to have a statement that says that one trigonometric expression is equal to another trigonometric expression. And what our job is to prove that that is in fact true. And the way that we do that is by simply working with one side of the equation, typically whichever side looks more challenging, more difficult, and doing identities or algebra to turn one side into the other side. And that's what we mean by verifying that that identity is true. So here's an example of an identity that's not one of our fundamental identities. But because of this, the fact that this is saying that these two quantities are equal to each other, we're believing that in fact tangent x plus cotangent x, regardless of the angle that I plug in, will in fact be equal to what happens when I multiply cosecant x and secant x. Now that doesn't seem too intuitive. It doesn't seem like it's something that we should automatically believe from our fundamental identities. So what we typically want to do is we want to go through a process of trying to verify. Now, the most important thing to recognize is that although this has an equal sign, this cannot be treated like equations. For instance, we can't move quantities from side to side by, let's say, subtracting cotangent x. That's a big no. Okay, we cannot move from side to side. Instead, all we can do is try to do whatever we can on one side. Let's say we start with the left side, and we start to apply fundamental identities, or we start to apply algebraic properties, or whatever we might do, basically based on how we, any methods we can think of in order to turn tangent x plus cotangent x into cosecant x times secant x. So let's take a look at a few steps of how we might be able to go through this process. Option that is often bypassed or forgotten about when we're verifying identities, because most people just think that they need to apply only the fundamental identities, is that they forget algebraic operations that are always possible. So here we have three different expressions that we could actually apply algebra on because of their form. So the first thing we should recognize is that tangent squared x minus 1 looks very similar to a squared minus b squared. And so I know that I'm able to factor a squared minus b squared into a minus b times a plus b. So sometimes it could be beneficial for us to factor a trigonometric expression into tangent x minus 1 times tangent x plus 1. And often the reason why it's beneficial to do this is because sometimes we're able to cancel out one of those common factors and make our life a little easier. So let's say we take a look at 1 over tangent x plus 1 over sine x. Well, that looks real similar to 1 over a plus 1 over b. And if I wanted to take these two terms, and perhaps the other side of the equal sign is a single fraction, then what I'm going to need to do is combine this into one fraction. So obviously what we would do is get a common denominator by multiplying top and bottom by b. Here, multiply top and bottom by a. And now we see that the denominator is going to be ab, while the numerator is b times 1 plus 1 times a. So we could do something really similar up top here, to where I realize that this needs an additional sine x. So we multiply top and bottom by sine x. Over here, this needs an additional tangent x. So we multiply top and bottom by tangent x. And when we finally combine, the denominator is going to be tangent x secant x, or I'm sorry, tangent x sine x, while the numerator is sine x plus tangent x. So combining fractions together, just like we would in algebra, factoring an expression just like we would in algebra. What about something like 1 over 1 minus cosine x? Well, this might not be too obvious at first. But I would like to remind you of a property of radicals that we often did whenever we had something like 1 over 1 minus the square root of x. And in a situation like this, where you want to rationalize the denominator, so you might think, well, I would have to multiply top and bottom by root x. And although that would cancel the radical here, it would not cancel the radical here. So the only thing we're actually able to do when we are trying to rationalize a binomial is that we multiply by the conjugate, which means the same expression, opposite sign. Which means that the numerator is simply 1 plus x, or 1 plus the square root of x, while the denominator turns out to be a difference of two squares, because it's a minus b times a plus b. So that gives us 1 minus the square root of x squared, which is x. So if you ever see a denominator with a binomial, not to say that this is definitely the process we should take, but sometimes this can help us, because if we do so by multiplying by the conjugate, that becomes 1 plus cosine x on top over 1 plus cosine x in the bottom. And so if we do that, notice that that gives us a denominator of 1 minus cosine squared x. And in the numerator, we have 1 plus cosine x. And now I'd like you to see why multiplying by the conjugate often helps. If I multiply a binomial times its conjugate, notice that it turns into an expression that looks like a Pythagorean identity. So that's why here we could eventually convert this into sine squared x, a single term. And the only reason that helped me was because of the fact that I multiplied by the conjugate. So one technique in verifying an identity is always do your best to try to do algebra at the beginning, or at least check the algebra, algebraic expressions, or algebraic properties that could be used. Whatever it is, trying to use algebra before jumping into the fundamental identities. The second tip that we should always pay attention to is to keep the goal in mind, or in other words, recognize what you're actually trying to achieve. So if I was to be given an identity like this, again, this is an identity, or apparently an identity, because of the fact that it says that these two sides are equal. So we always want to try for the more difficult side, or the side that has more things to do to it. So if I was looking at this at the beginning, I'd recognize, man, there are 3 different trigonometric functions on the left and only 1 on the right. I'd also realize that it would be pretty difficult, or it seems like it would be pretty difficult, to somehow turn a single cotangent function with a constant into 3 different functions over on the left. So I'm already starting to think that the left side is a great place to start. But when we say keep the goal in mind, what that means is pay attention to the fact that I need to turn the left side completely into cotangents. So I need to search for cotangents somewhere in the problem. And so if I continue to see cosines, or I continue to see sine, or I continue to see cosecant, those have to be changed. So that's what we mean by keep the goal in mind. So let's go ahead and try to work through this. So we always work with one side at a time. So why don't we start with some algebra? We get cosecant theta times cosine theta plus, and over the second term, we get cosecant theta times sine of theta. And as you work through the problem, you should hopefully be paying attention to what the goal is. You see how in the left side, I had one single term with parentheses, but now on the right side, no more parentheses. Secondly, I had one single term because it was all factored, while on the right side, I had 2 terms that were being added. And so all within the first step, notice that I now have 2 terms that are added. So I'm keeping the goal in mind. I'm already recognizing that it's starting to look closer to what it's supposed to. So my guess is that one of these terms is going to be able to turn into cotangent theta, and one of them will be able to turn into 1. And our job is to figure out which one to do. Now, although we haven't quite gotten to what the third step is, the third step is to apply fundamental identities. So notice in this case right here, I don't see any other algebra that I could really use. So I'm going to do my best to start trying to convert this into some other form. So if I were to convert this, I can apply some identities. So for instance, the first thing I'm starting to think is that maybe it would be a good idea to rewrite cosecant of theta as its reciprocal function. Another reason why I'm starting to think that is I know that since I see sines and cosines, I'm remembering that cotangent of theta is cosine theta over sine theta. So I'm trying to find those somewhere. So the first thing I would do here is I would replace cosecant theta with 1 over sine theta. And I would replace this cosecant theta, of course, with 1 over sine theta as well. And that's multiplied by cosine theta. This is multiplied by sine theta, and I'm still adding. So I'm not done because it doesn't look like the other side. I'm also not done because I don't see any cotangents. I'm keeping the goal in mind. I'm recognizing what I'm trying to achieve. So this is where, again, I'll just do a little algebra. Let's distribute that so that I get single fractions, and that gives me cosine theta over sine theta. While over here, this gives me sine theta over sine theta. I'd like you to also recognize that I have never once touched the right side. And since I haven't touched the right side, my goal is to turn the left side into the right side. So I should only be working with one side and not shifting things from side to side like I would in a regular equation. Okay. And so now, go. So now at the last step, I should recognize that cosine theta over sine theta is in fact cotangent theta. And I should also recognize that sine theta over sine theta is 1. And I have now completed my proof. Sometimes we can put a little square at the end just to show I've done my proof. So the point of an identity is not to solve anything. The purpose of verifying an identity is to go through the process of algebra and trigonometric identities to show how, in fact, that crazy left side becomes the right side. This next step then, as we've already shown on a prior identity, is to apply the fundamental identities. And we mean our reciprocal identities or our Pythagorean identities. Perhaps if there was a negative angle, we could apply our even-odd identities or our quotient identities. So let's say that we have this relatively straightforward identity. Now this again is not a fundamental identity. Cotangent x times sine x is supposedly equal to cosine x. And I say supposedly because there's an equal sign, but I don't know for sure. So I'm going to verify that this identity is correct. So let's start off with what we do not do. What we are not allowed to do is say, hey, if I divide by sine x, then that must mean that the sine x cancels, giving me cotangent x equals cosine x over sine x. And although that seems true, because it's a quotient identity, this is the wrong form for being able to verify an identity. Because what I've just done is I've expected already that the equation must have been true. So I went ahead and did properties of algebra to solve that equation. I divided both sides by the same quantity. The problem is I don't know that it's true. So what I need to do is I need to simplify. So I should definitely say this is wrong. Okay. Instead, we want to verify the identity by working with one side and turning it into another. Okay. So in this problem right here, again, you always start with the side that looks like there's more to do. it would be quite difficult to turn a single basic trigonometric function into the product of two other ones. So instead, I start with the left side and I start to think of an identity that I could use. So there's a few identities. I mean, obviously I could replace cotangent x with 1 over tangent x. That's an identity. And then I multiply by sine x. But notice I'm not keeping in mind the goal. My goal is to somehow get cosine x. So although I could have used that identity, that quotient identity, or the reciprocal identity, it didn't help me because I don't see any cosine x's still. So this is why it would have been a better option to use our quotient identity by converting cotangent x into cosine x over sine x. And now the reason that cotangent x times sine x is equal to cosine x is because when I use that quotient identity, the sine x's cancel, leaving me with cosine x, and therefore I have proven the identity. So we should always start by using algebra. Once you think you've exhausted the algebra or you don't see any other methods that you could do, then you go ahead and try to go to fundamental identities. But it also, you don't have to go in that order. Sometimes you apply an identity first, and then you start to apply the algebra. There's various ways to go about this process. So let's look at another more complicated example. Before revisiting the first identity that we wrote at the beginning of this lesson, the fourth, and I feel the last identity there, the last rule that we should think of is what I often tell my students year after year: do not sit and stare, try something. There's always something to do. There's always some sort of identity to apply. If you can't think of an identity to apply, then there's always a reciprocal identity you can apply. You could always change things into sines and cosines, because a lot of times it's easier to turn into sines and cosines, which is what we saw up in example 3. When you can't figure out a good identity to use, just convert everything to sines and cosines. It should typically be a last resort, but you'll find a lot of the times that turning into sines and cosines makes it, makes it a little easier to deal with. But the worst thing that you could do is just look at it and say, I don't know what to do. There's always something to try. You just keep the other side in mind and keep trying to get it closer. So let's take a look at this one. I encourage you to pause the video and try this on your own and see if you can get one side to become the other. I'll give you a little tip about two sides. You see on the left side here, I see 2 terms. On the right side, I see 1 term. It is always easier to combine 2 terms into 1 than it is to turn 1 term into 2. Because if I was going to turn 1 term into 2, I'd have to first of all figure out, how do I split this fraction apart, or how do I split this expression apart? But with combining them, there's easy ways to do this if we just apply some identities. So the first thing I'm going to realize is cosecant x and secant x, those are reciprocals of sine and cosine. In addition, tangent x and cotangent x can also be put in terms of sine and cosine. So the starting point for me is, let's convert tangent x and cotangent x into sines and cosines. So this is sine x over cosine x plus, and now cotangent x is cosine x over sine x. But again, it doesn't really give us too much of how to get 1 term here. And so think about it, if I've got 2 fractions, the only way to combine those fractions to become 1 term is by doing algebra. Get a common denominator. So I could see that this side over here is going to need an extra sine x over sine x, while the right side is going to need another cosine x over cosine x. That way the denominators are the same, and not only that, it's 1 single fraction. It's 1 single term. So the denominator becomes sine x cosine x, while the numerator, take a look there, is sine squared x plus cosine squared x. Now, whenever you see quantities being squared, you think of two things. You either can think, maybe I can factor this as a difference of two squares, but it's not a difference. And even if it was, it looks like factoring wouldn't necessarily make the problem easier. But what I should definitely see is that sine squared x plus cosine squared x is the same as 1. By the Pythagorean identity, we know that it's equal to 1. So that's something we should always think when we see quantities being squared, is that maybe there's a Pythagorean identity to use. So this is nice, but the thing is it's still not quite to the place that we need it to be. It's better. Instead of it being two terms, it's now one single term. Instead of it having tangents and cotangents, it now has sines and cosines. And now this is where sometimes looking to the other side can give you a little tip. Okay, so this is where I'm going to just write a hint at this point. Okay, and in fact, I'll just put it this way, that this is the hint. Okay, so the hint here is that cosecant x is the reciprocal of sine x, and that secant x is the reciprocal of cosine x. So this gets back to using the goal of my problem. I'm trying to convert into cosecant x and secant x. Well, if I know that cosecant x is 1 over sine x, and I know that secant x is 1 over cosine x, if I multiply those, I get right to here. So that's why the next step might be to rewrite this as 1 over sine x times 1 over cosine x. And now using the Pythagorean identity, the reciprocal identities, we can see that my final result is cosecant x times secant x, which is the side that I needed to turn it into. So this was just a little bit of side work to help me to look at the other side and keep in mind what our goal is and what we're trying to turn it into. But notice, I'd like you to realize this is not my answer. My answer is not cosecant x times secant x. All that is the end of my proof. The answer is this. The answer is all of the work. The answer is the process that we take to get it from one side to become another side. So in general, when we move into calculus, we're not going to be given the other side. We might only be given tangent x plus cotangent x, and that's difficult to deal with within the context of the problem we're working on. So instead, I do all of this work to see that it becomes the same thing as cosecant x times secant x, which may or may not be easier for us to deal with. But that's essentially what's going to happen, is that in these problems, you're given two sides and you need to turn one side into the other. We'll do one last more complicated example here. So the first step we should always take is making a decision of what side looks like there's more to do. So it's very possible that I could start with the left side. It looks like there's quite a few terms, 3 terms in the numerator. But it seems that changing secants and tangents into sines and cosines will in general be easier than taking sines and cosines and turning them into tangents and secants. So I'm going to start with the left side and hopefully convert into whatever the right side is. So the first thing I notice is that there are a few secant x and tangent x show up together inside of a Pythagorean identity. So sometimes it might be beneficial for us to apply an identity or do something to force that identity to occur. But because I'm trying to get all sines and cosines, the first thing I think to do here is that I'm going to convert this into 1 over cosine x plus sine x over cosine x. And then I'll get the same terms in the denominator. The only difference is it is subtraction now. So that'd be 1 over cosine x and sine x over cosine x. So now I see a complex fraction. So this takes us back to another piece of algebra that's really beneficial. Since I want to get rid of the complex fraction, and in the numerator I see denominators of cosine x, and in the denominator I see denominators of cosine x, it looks like if I multiply top and bottom by a cosine x and distribute to every term, then all of those cosine x's are going to disappear. Which means that once we distribute, we're left with 1 plus sine x over 1 minus sine x. Now, before moving too far ahead, I'd like to take a look at what our goal is. Our goal is to make this happen. The thing that's nice is I already see a 1 plus, like I'm supposed to. And I also see a sine x, but I see other terms involved up here. Likewise, I need to somehow get a cosine squared x in the bottom, and I don't see anything being squared in the bottom. And I see sine of x. So I'm going to remember an identity that says sine squared x plus cosine squared x is equal to 1. So if I'm supposed to get cosine squared x, then that must mean that cosine squared x is the same thing as 1 minus sine squared x. So that hopefully gives us an indication of what we might do in this denominator. I need to somehow get 1 minus sine squared x to show up, because that will turn into cosine squared x, which is what we needed in our problem. So I'd like you to think about what you would need, pause the video for a minute, and think about what would you need to do in order to take 1 minus sine x and make it 1 minus sine squared x. So it turns out that multiplying by the conjugate, which is another algebraic process that's going to get us to where we need to be, over itself, because I have to multiply by a factor of 1 or else I'm changing the function. And now if I do so, notice that this just becomes 2 binomials that I can multiply together. And so the numerator becomes 1 plus sine x plus sine x plus sine squared x. And at this point, we should really start to feel happy and proud of ourselves, because look at how the numerator automatically turned into what it was supposed to. But the denominator is turning into 1 minus sine squared x. Okay, by expanding and multiplying to become the difference of 2 squares, the negative sine x and positive sine x cancel. And as our last step, again, keeping the goal in mind, always knowing where we're supposed to be, this gives us 1 plus 2 sine x plus sine squared x in the numerator. And in the denominator, 1 minus sine squared x is the same as cosine squared x, which is exactly what we needed to show up in the denominator. So we have now forced the left side to turn into the right side. And we have just verified our identity. That indicates that we have completed our proof. There is never one right way to do things. It's very possible that maybe you chose to do this in a different way and maybe it would have worked. But what we really need to make sure to do is to follow these kind of step-by-step guidelines. And it doesn't, like I said, it doesn't always have to be in the same order as the steps I gave. You could maybe do fundamental identities first, followed by algebra, or do algebra first, followed by some identities, or mix it up a little bit. But at the end of the day, the most important rule here is don't sit and stare. Try something and keep the goal in mind.